Every planet in the solar system stands up. One of them is lying down. Uranus is tilted 98 degrees. It does not spin, it rolls. And because it rolls, something happens on that world that happens nowhere else in the solar system. Point one of its poles at the sun. Now hold it there, not for a day, not for a season. For 42 years. 42 years of sunlight that never sets. And then, when the planet finally swings around, 42 years of darkness that never lifts. An entire human lifetime could pass at the North Pole of Uranus without a single sunrise. On that planet, the word day means almost nothing. Something did this. Something reached into the early solar system and knocked a world 4 times wider than Earth onto its side, and left it rolling like a barrel through the dark. And it left evidence behind, in the moons, in the magnetic field, in a temperature that should not be possible. 3 suspects, and 40 years after we collected that evidence, someone went back and found something wrong with it. We have visited Uranus exactly once. On the 24th of January 1986, NASA's Voyager 2 passed roughly 81,500 kilometers above the cloud tops. It had 5.5 hours of close encounter. Then it kept going and never looked back. Everything humanity knows about that planet from close range comes from those hours. And what Voyager found was worse than a tilted planet. The magnetometer team, led by Norman F. Ness, reported the results in the journal Science in 1986. Uranus has a magnetic field, but the field is tilted 59 degrees away from the planet's rotation axis. And it isn't even centered. The source of the field sits offset from the middle of the planet by about 1/3 of Uranus's radius. Think about what that means. On Earth, magnetic north and true north are close enough that a compass is useful. On Uranus, the magnetic field is roughly perpendicular to the spin and shoved off to one side. The field strength at the cloud tops varies by up to a factor of 10, depending on where you stand. A tilted planet is a mystery. A tilted planet with a broken, off-center magnetic field is a crime scene. To understand how strange this is, you have to understand how long Uranus has been getting away with it. William Herschel found the planet on the 13th of March, 1781. He wasn't looking for a planet. He thought he'd found a comet. It took months of argument before astronomers accepted what he'd actually done, doubled the size of the known solar system in one night. That was 245 years ago. In those 245 years, Uranus has completed fewer than 3 orbits. 1 year on Uranus is 84 Earth years. Herschel died without seeing the planet he discovered return to where he found it. The planet sits about 2.9 billion kilometers from the Sun. Sunlight out there is roughly 400 times weaker than it is on your skin right now. At noon on Uranus, the Sun is a bright star, not a disk, a point. And it is cold in a way that has no comparison on Earth. Uranus holds the record for the coldest temperature ever measured on a planet in this solar system, about -224 degrees Celsius in its upper atmosphere. Colder than Neptune, which sits 1.5 billion kilometers farther out. That should not be possible. A planet closer to the Sun should be warmer than one farther away. Hold on to that. It matters later. Now put the tilt back into the picture. Because Uranus is lying on its side, its seasons are not like ours. On Earth, the tropics get the most sunlight and the poles get the least. On Uranus, that flips. Over the course of one 84-year orbit, the poles receive more total solar energy than the equator does. And yet the equator is not the coldest part of the planet. The temperature map doesn't match the sunlight map. The atmosphere is redistributing heat in a way we still cannot fully explain. Winds there reach speeds of hundreds of meters per second. Something is moving energy around that world, and we do not have the data to say what. And then there is the moment the seasons turn. Twice per Uranian year, once every 42 Earth years, the planet passes through equinox. For a brief window, the Sun crosses the equator, and both hemispheres get light at the same time. The last one was in December 2007. Astronomers had been waiting decades for it. When it came, the planet woke up. Ground telescopes and Hubble recorded bright cloud features appearing across a world that had looked, for most of the Voyager encounter, like a featureless ball of pale green. Storms, bands, structure that hadn't been visible before. The atmosphere had been there the whole time. We just hadn't been watching during the part of the year when it does anything. That's the shape of the entire problem with Uranus. Our observations are snapshots. The planet's clock runs in units of 42 years. We are trying to describe a life from a handful of photographs taken at random. We have 5.5 hours of close-range measurements from the only spacecraft that ever went. That's what we're working with. The people trying to solve this are not doing it with a spacecraft. They're doing it with telescopes, archives, and mathematics. In 2018, Patrick Irwin, a planetary physicist at the University of Oxford, pointed the 8-meter Gemini North telescope on Mauna Kea at Uranus. He wasn't chasing headlines. He was chasing a spectral signature in a narrow window of infrared light between 1.57 and 1.59 micrometers. The instrument was called NIFS, the Near-Infrared Integral Field Spectrometer. It sampled sunlight reflected from a thin layer just above the main visible cloud deck. What Irwin's team found, published in Nature Astronomy on the 23rd of April 2018, was hydrogen sulfide, between 0.4 and 0.8 parts per million, sitting above the clouds. Hydrogen sulfide is the compound that gives rotten eggs their smell. If a human being could somehow descend into the cloud tops of Uranus and survive the temperature and the pressure and the lack of oxygen, the last thing they would notice, before everything else killed them, is the smell. That detection is not a joke, it's a fingerprint. Jupiter and Saturn have ammonia in their upper clouds. Uranus and Neptune have hydrogen sulfide instead. That difference tells us these two worlds formed somewhere colder or farther out, or at a different time than the gas giants did. Uranus is not a small Jupiter, it's a different kind of object entirely, and it has been tilted over almost since the beginning. So, something knocked it over. Here is the problem with saying that. Planets do not tip easily. Uranus is 14.5 times the mass of Earth. To rotate that much matter through 98 degrees, you need to deliver an amount of angular momentum that is difficult to imagine and even harder to explain. A spinning body resists being turned. That's why a bicycle stays upright and a spinning top refuses to fall. Now scale that up to 87 billion trillion tons of hydrogen, helium, water, methane and ammonia, rotating once every 17 hours. You cannot nudge that. You cannot tilt it gradually with a small push. Whatever changed the axis of Uranus had to be, by any measure available to us, one of the most violent events in the history of this solar system, or one of the most patient. There are 3 leading suspects. They contradict each other, which means, at most, one of them is telling the truth. And the way you tell them apart is not by looking at the planet. It's by looking at what the planet is carrying with it. Suspect 1. A single, catastrophic impact. The classic explanation. Early in the solar system's history, a protoplanet, something in the range of 2 to 3 Earth masses, struck the young Uranus at an oblique angle and rolled it over. Simulations support this. Work, published by Jacob Kegereis and colleagues at Durham University in 2018, modeled these collisions in detail and found that an oblique strike by a body of that size can indeed produce the tilt we see. The same impact would eject debris into orbit, debris that could go on to form the moons. That's elegant. One event explains the tilt and the moon system at once. But there's a problem. Uranus has 29 known moons, the most recent one confirmed by the International Astronomical Union in March 2026. A rock 10 kilometers wide that the James Webb Space Telescope found hiding in a system Voyager 2 had already photographed. And the 5 large ones orbit almost exactly in the planet's tilted equatorial plane. They are tipped over with the planet in near-perfect formation, moving in the same direction Uranus spins. If you knock a planet over in one violent instant, the moons that form afterward should record that violence. Instead, they sit in a disk so orderly it looks like nothing ever happened. A single impact is fast. Moon systems are slow. Getting a tidy, prograde, aligned family of moons out of one catastrophic collision is much harder than it sounds. It gets worse. Several analyses point out that if a single impactor delivered the tilt, The resulting satellite system would be expected to end up orbiting backwards relative to the planet's spin. Uranus's moons do not orbit backwards. They orbit forwards, with the planet, exactly as if nothing dramatic had happened to them. The tilt says violence. The moons say order, except for one of them. Miranda is the smallest of Uranus's 5 major moons, roughly 470 kilometers across, a body you could drive around in a few days if it had roads. Voyager 2 photographed it in January 1986 and returned an image that planetary scientists have been arguing about ever since. Miranda looks assembled. Its surface is a patchwork of unrelated terrains, slammed against each other, cut by enormous canyons and stacks of parallel ridges called coronae. It does not look like a moon that formed and then aged. It looks like a moon that was taken apart and put back together by someone in a hurry. And on one side of it stands Verona Rupes, a cliff face roughly 20 kilometers high, the tallest known cliff in the solar system, 10 times the depth of the Grand Canyon, standing vertically on a body 470 kilometers wide. Miranda's gravity is so weak that if you stepped off the top, you would fall for about 12 minutes before you hit the bottom. Something happened in that system. Miranda is the only witness that still shows the bruises, and it isn't telling us who. Suspect 2, more than one impact. So the tilt happened in stages, 2 or more large strikes, spread out over time, each one nudging the planet further over. Between the strikes, the disk of debris around Uranus would have time to settle back into alignment with the planet's new equator. The moons form from that resettled disk. They inherit the order, not the chaos. This scenario was explored in detail by Alessandro Morbidelli and colleagues in 2012. It solves the moon problem. It creates a different one. You now need multiple Earth-scale objects to hit the same planet, at the right angles, in the right order, in a solar system that was already running out of Earth-scale objects to throw. Each collision is unlikely. Requiring several of them multiplies improbability by improbability. Some of the follow-up analysis has not been kind to the original version of this model. It may still be right, but it asks the universe for a very specific run of bad luck. Suspect 3, no impact at all. This is the strangest one, and in some ways the most unsettling. In 2022, a team led by Melaine Sayenfest at the Paris Observatory published a paper in Astronomy and Astrophysics with a title that says it plainly: Tilting Uranus via the migration of an ancient satellite. The idea is this: moons don't stay where they form. Tides between a planet and its moon push the moon slowly outward. Our own moon is drifting away from Earth at roughly 3.8 centimeters per year. Over 1 billion years, that adds up. Now imagine Uranus had a large moon, a massive one. As it migrated outward, its gravitational pull on the planet's spin axis could have swept the planet into what's called a secular spin-orbit resonance, a kind of gravitational rhythm where small tugs, arriving perfectly in time, accumulate instead of cancelling out. Push a swing at the right moment every time, and a child's arm can lift an adult. Under this model, nothing ever hit Uranus. The planet was tipped over gradually, over hundreds of millions of years, by a moon that was doing nothing more violent than drifting away. And here's the part that stays with you. That moon is not there anymore. For the model to work, the satellite has to be lost, destroyed, ejected, or torn apart after the job is done. The culprit removed itself from the scene. We would be looking at a planet knocked over by something that no longer exists, leaving no crater, no debris, and no witness. Only the angle. 3 suspects. A single impact that can't explain the moons. Multiple impacts that ask too much of chance. And a vanished satellite that leaves no evidence at all. And there is one more piece of evidence sitting on the table that we have not accounted for. Go back to that magnetic field. Tilted 59 degrees, anchored a third of the way off-center, varying tenfold across the surface. Earth's magnetic field comes from a dynamo in the liquid iron core. Deep, central, and roughly symmetric. That geometry is why our field looks like a simple bar magnet. Jupiter and Saturn do the same thing with metallic hydrogen. Uranus does not. In 2004, Sabine Stanley and Jeremy Bloxham published a paper in Nature proposing an answer. They ran numerical dynamo models and found that if the magnetic field is generated not in a deep core but in a thin outer shell of conducting fluid, wrapped around a stably stratified, non-convecting interior, the model produces exactly the kind of messy, off-axis multipolar field that Voyager measured at Uranus and Neptune. In plain terms, Uranus may not have a churning core at all. The engine that makes its magnetic field could be a shallow layer near the surface, sloshing around an interior that has stopped moving. Now hold both facts at once: a planet knocked onto its side, and a planet whose insides may have settled into layers that no longer mix. Those two things might be connected. A violent enough event doesn't just change a planet's angle, it changes its temperature profile, its internal structure, the way heat can escape from the center. It could stratify a world, shut down its convection, leave the interior locked in place while only the outer skin keeps stirring, which would explain why Uranus is the coldest planet in the solar system, despite not being the farthest. We cannot prove it, not with the data we have, and that data is about to become the real story. Because in 2024, someone went back and looked at the Voyager 2 data again, not the pictures, the conditions. Jamie Jasinski, a space physicist at NASA's Jet Propulsion Laboratory, led a study published in Nature Astronomy in 2024, examining what the solar wind was doing around Uranus in the days before Voyager arrived. The solar wind is the stream of charged particles constantly flowing outward from the Sun. It presses on planetary magnetospheres the way wind presses on a sail. Most of the time at Uranus, that pressure is gentle. The planet is nearly 3 billion kilometers away, and the wind out there is thin. In the week before the 1986 flyby, the dynamic pressure of the solar wind at Uranus increased by a factor of 20 times. Uranus's magnetosphere collapsed inward. It went from an estimated 28 planetary diameters across to roughly 17. The plasma inside it was largely swept away. The radiation belts were driven into an extreme state, and then, into that compressed, emptied, distorted bubble flew the only spacecraft humanity has ever sent. Jasinski's team calculated how often Uranus's magnetosphere is in a state like that. Less than 5% of the time. Read that again. There was a better than 95% chance that Voyager 2 would have seen something completely different. If it had arrived a few days earlier, our entire textbook picture of this planet would be a different picture. We didn't measure Uranus. We measured Uranus having one of the worst weeks of its century. Think about what that does to everything you have heard so far in this video. The tilted magnetic field, the tenfold variation in strength, the off-center source, the emptied radiation belts. Every one of those measurements was taken inside a magnetosphere that had been crushed to roughly 60% of its normal size a few days before the spacecraft arrived. Jasinski's team put it plainly: the interpretation of Uranus's magnetosphere as extreme may simply be an artifact of a flyby that happened under extreme conditions. 40 years of textbooks, 40 years of the weirdest planet in the solar system, built on a 5.5-hour glimpse of a world in an abnormal state that we had no way of recognizing as abnormal because we had nothing to compare it to. And this is not the only thing we got wrong. For nearly 40 years, one of the most repeated facts about Uranus was that it has no internal heat. Jupiter, Saturn, and Neptune all radiate substantially more energy than they absorb from the Sun, leftover warmth from their formation, still leaking out. Voyager's data suggested Uranus radiated essentially nothing extra. A dead planet, a cold rock with clouds on it. In July 2025, a team including Xinyue Wang and Liming Li at the University of Houston published an analysis in Geophysical Research Letters combining spacecraft data, ground-based observations, and modern modeling. Uranus does have internal heat. It emits roughly 12.5% more energy than it receives from the Sun. It's still far less than its siblings, which run upwards of 100%. But it is not zero. The planet is not dead. It has been quietly leaking warmth this entire time, and we filed it as a corpse because we caught it at the wrong moment with the wrong instruments. And in April 2025, a team led by Laurent Lamy using more than a decade of Hubble observations to track Uranus's aurorae, published a new measurement of the planet's rotation period in Nature Astronomy. A day on Uranus is 17 hours, 14 minutes, and 52 seconds. That is 28 seconds longer than Voyager told us. It sounds trivial. It is not. Over 40 years, a 28-second error compounds until you can no longer say which side of the planet you are looking at. Every coordinate we had assigned to features on that world had slowly drifted into meaninglessness. So here is the uncomfortable question this video has been walking toward. We have been calling Uranus the most broken planet in the solar system. What if it isn't broken? What if we simply looked at it once, for 5.5 hours, on a bad week, with 1970s instruments, and then spent 40 years describing what we thought we saw? There is a way to settle this. It has a name, a price, and a schedule. In 2022, the US National Academies published the Planetary Science Decadal Survey, the document that sets the field's priorities for 10 years. Its highest-ranked recommendation for a new flagship mission was not Mars. It was not Europa, it was Uranus. The concept is called the Uranus Orbiter and Probe, an orbiter that would stay for years instead of hours, and an atmospheric probe that would descend into the clouds and transmit until the pressure destroyed it. Estimated cost, roughly $4.2 billion. For fiscal year 2026, Congress allocated $10 million to formulate it. $10 million against $4.2 billion. That is not a mission, that is a study of a mission, and there's a clock. Reaching Uranus efficiently requires a gravity assist from Jupiter, and those alignments are not always available. The current concept targets a launch no earlier than 2031, with arrival at Uranus no earlier than 2044. Do the arithmetic on your own life. If that spacecraft launches on schedule and survives the cruise and arrives on time, the people who first proposed it will be in their 70s and 80s. Some of the graduate students who wrote the supporting papers will be retiring the year the data comes back. Patrick Irwin found the smell of that planet in 2018. Jamie Jasinski found the flaw in our only close-up in 2024. Sinyue Wang and Liming Li found its hidden warmth in 2025. Laurent Lamy found the true length of its day. Every one of them is working on a planet they may never see clearly. That's what planetary science asks of people. You do the work knowing the answer arrives after you've stopped waiting for it. Herschel discovered a world and died before it finished a third of one orbit. The pattern hasn't changed in 245 years. We are, right now, in the longest gap in the history of ice giant exploration. Voyager 2 left Uranus in 1986. If everything goes perfectly, the next visitor arrives in 2044. 58 years between the first look and the second. Picture it one more time. A pale blue-green world, 4 times wider than Earth, rolling on its side through 3 billion kilometers of darkness. One pole facing a sun that is barely a star, holding that face for 42 years without blinking. A magnetic field pointing the wrong way, anchored somewhere off-center inside the planet, wobbling as it turns. Clouds of frozen hydrogen sulfide, and a slow trickle of ancient heat still escaping from a formation that finished 4.5 billion years ago. And somewhere behind all of it, an event we cannot name. A collision, a series of collisions, or a moon that pushed and then disappeared. We have never gone back. We have one bad week of data, 4 decades of assumptions, and a growing suspicion that most of what we said about that planet was really a statement about our own limitations. There's something almost human in that. We look at a thing once, under bad conditions, and we call it broken. Then we build an entire understanding on top of that first impression, and we defend it for 40 years, because going back is expensive, and the answer would take a lifetime to arrive. The universe is patient with us. It keeps the evidence exactly where it is, tilted 98 degrees, waiting. Uranus isn't broken. We just met it on a bad day. Thanks for watching, and I'll see you in the next one.